actual devices that usually we refer to as the apparatus, meaning transformers and machines. So transformer is probably the easiest one because there is no moving parts. So the concepts are fairly easy. And a lot of this concept I already covered on the electromagnetics, but we're going to review that again once we get to it. But just to give you guys a quick idea. Let me see. Okay, so power transformers. Transformers. There's all kinds of transformers, by the way. There is current transformers. There's potential transformers. There's power transformers, and there's other types that are used in the industry. And some of the ones that are actually starting to merge now, and I'll mention them along the way, but really this class is focusing on power transformers, transformers that are designed to transfer energy from the primary to the secondary side. And really the main goal of it is to step up and step down voltages on a power system. And I think I talked about it right at the very beginning. This whole idea of the whole concept of generation or generating facilities, generating stations and load, and in between you have a transmission system. So in order to do that, obviously we're required to use transformation. So power transformers, depends on the voltage level. They can range from as high as 765 kilovolts. And when I say 765, I'm talking about from line to line. I will talk about it in more details. Then to smaller transformers, 240, 120, which is what you find, right at the pole or by your house. This is what you have when they feed you at your house. And as I said, they're really just to transfer power from one voltage level to another. And obviously current obviously changes as well, right? And we'll get through that. So is the ability, is inexpensive, we say, to change voltage is the key thing or the key advantage in AC systems. So is obviously, when we're talking about transformers, and I'll give you guys some ideas about, how much it would cost. But when we're talking about transferring power, it's probably the most inexpensive way to move energy or to transfer power and to from the generating station to the load center. They're very efficient. Transformers are in the 99% efficiency, meaning you only have very, very small losses. But again, we're talking of very large, in some cases, transformers that can be up to 250 MVA, and that's a lot of power, right? So even at that NVA level, you're still losing kilowatts, right? But in comparison, when you compare the losses versus what you are able to transfer from one side to the other, you're in the 99% efficiency. There's a lot of things that have been discussed lately, and I think I mentioned to you, and then when we go through the equations, we're going to go through the equation, just a simple transformer design. I'll mention it again, but the most recently companies have been, well, I wouldn't say companies, the industry in general, have been looking at, is there any other way that we can do this transformation where there is some things that we can take advantage that we might not be able to do with transformers as we know them, right? Because these are passive devices, meaning there is no moving parts there. So the only thing you can do is step voltage up and down, but you cannot regulate frequency. You cannot control power factor. There's nothing you can do. It's what we call a passive device. As I said, most recently, there's been a lot of discussions. You can Google it as a matter of fact to find if you have an interest. Not that we're going to discuss it, but maybe in your power electronics class you want to discuss it. But most recently, the Department of Energy, this is about, about 6-7 years ago, they have been working on what they call the digital substation concept. One of the things that they talk about was, okay, so we have these devices, and there's a lot of things that we can do, but there's a lot of other things that we now required to do that we cannot, because once again, we don't have that ability. There are no controllable devices. to some degree. There are some controls, and I'll talk about it once we get to that. I'll show you some of the controls that are present on very large transformers, as a matter of fact. Plus, the idea is to use solid state. So instead of using passive devices, use the active devices where you have an active control. So, yes.
Would these be like switching regulators, that kind of thing?
Correct.
Coming out of FETs?
Correct. So basically what you do, and the nice thing about it is, if you use power electronics, and like I said, if you Google it, you'll find it. As a matter of fact, there's a couple of companies now that are actually in business. I don't know how much business they're getting, but they're in business. You'll hear this term, is solid state transformer, or known as SST. Okay. So what the Department of Energy has been wanting to do, once again, they were pushing, the last administration, actually it started with the Obama administration, was to, hey, are there other things that we can do if we were to utilize power electronics and have transformers that have the ability to push power in both directions, right? What we call bidirectional power flow. Can you control power factor? Can you correct harmonics? There's a lot of other things. Can you mitigate sags and swells, whatever type of power quality issues that we encounter in the system? Can we use a transformer? Passive transformer doesn't have that ability. It's just a winding with a core, and as simple as it might sound, it's actually a pretty complex device. But you guys might come across this. There's companies, like I said, that are already looking into it. Right before I left SCE, the group that I was with, we put together a proposal with the Department of Energy to install a DC line, take an AC line and convert that AC line into a DC line, and we're gonna test some of this solid state transformers. And there's a whole bunch of different flavors that these things come. Not new concept, as I said, there's a company called ABB. ABB actually came up with this solid state transformer back in the, I want to say, mid 2000s. And the challenge is that they're very expensive, and the key thing, they're not as efficient, because you incur a lot of losses on the power electronics, right? Because you have this very high frequency switching devices, and that means a lot of heat, right? So yeah, you can get a lot of the, so just like I said, you can mitigate a lot of the power quality issues that we find on the system, but it's a question of cost, really, at the end of the day. That's really the cost makes, the argument. The answer is right now, as we speak, no, not yet. The project that I mentioned to you guys that we're working with a company in Korea called Haiku Electric. And Haiku Electric has, a version of it, and then the Korean government has actually been testing it. The one thing that I can tell you, and you can, like I said, you can Google it. China is doing a lot of this work. The same with China is that, even we ask questions, they won't give you the answers, right? They don't want to share a lot, but they're using a lot of power electronics now and this kind of concept of like solid state transformers. And when I get to the question, I'll put a note there that I'll remember to mention sizes, because that's the other thing. If you use power electronics, the idea is that you can reduce the size and the physical size, so per MVA, so it has a lot higher what we call energy density, and we'll talk about that. But again, losses. If you get a chance to work, and by the way, we use power electronics in the industry already. There is a lot of devices that we utilize in the electric industry, especially utilities, with high voltage power electronics. And when I mean high voltage, I'm talking about in the range of the 100 to 150 kilovolts. So we have, we call them FACS devices, flexible AC transmission systems. And the challenge with it is the cooling. And a lot of these devices that we have in the industry, we utilize, the utilities utilize, they have to have liquid cooling. So we don't have to worry about this here, right? Because there is some liquid, we'll talk about it, but not in the sense that that you gotta do on protecting power electronics. Traditional transformers, so we have low voltage. So the low voltage, and I think I talked about this at the very, very beginning, so starting from 120 volts. You can go all the way up to 34.5 kilovolts, and I still consider high voltage. Low voltage, I'm sorry. High voltage starts at about 69 kV, line to line, all the way to 230 kilovolts. And this is the IEEE definitions. That's how they define voltages, okay? Then we have extra high voltages, 735, 500, 765. I think once again, I mentioned that at the very beginning too of this class, the very first set of slides that I put up here. And I said, in the United States, we don't have any voltages above 765. In other words, we don't have any ultra high voltage in the United States. That's only in China. I think Brazil might have now ultra high voltage, or what we call UHV. Somebody told me Japan, but I haven't even looked into it, so you guys might want to Google. So in the United States, basically, we stop at 765. And that's on the eastern side, border with Canada, when there is quite a few now. By the way, there's a lot of buildup on 765. There is some pictures that I have for you of a company that I work with that manufactures transformers, and they're building a lot of 765 for the Eastern Interconnect. There's a lot of companies, they're upgrading their 765 network, but that's as high as we go. And those are line-to-line voltages, remember. Then we have generation voltages. Those are step-up transformers from 600 volts all the way to 25 kilovolts. By the way, these transformers are very special transformers, and I mean special in the design. They have to be a lot beefier and a lot more, you have a lot more iron and copper. Reason being is because when you have a fault, you're right next to the source of fault current, which is the generator. So the faults are pretty high, and the forces that those transformers incur are, if you just use a typical substation transformer, might not survive. So there's a special design for generating stations or power station transformers. And then I put some voltages for you. I don't have to go through that, but those are the voltages that you will encounter. And people may ask, why do we have so many voltages? Why can't we just pick 4 or 5 and that's it? Reason being is because the system has evolved for the last 150 something years. And as the system was evolving, there were not standards per se, right? So Southern California Edison, PG&E, or the companies that made it up will say, we're going to pick this voltage. We think this is a good distribution voltage, and they will pick that voltage, right? So we ended up with a whole. But if you look at it now, we're a lot more standardized, especially on the transmission. 765, 500, 230, those are by far the most predominant voltages in the US. So we got to step up and step down, right? Starting from the most common design is very simplistic, which is your single phase pole mounted transformer. These are the ones that you see up on the poles, right? I know you won't miss them. The little number there is like telling you the kVA. In this area, we have a lot of 25. There's a lot of 25 kVA, so be careful, especially now driving. But when you look around, just if you pay attention, you'll see those markings, and that basically is telling you the kVA. So those are kVA, right? But these are oil field transformers. And you can, and we'll, as I said, we'll get into the more details, but you can see right, the bushes on the top is the high voltage side, bushing on the bottom, this right here is the low voltage side, right here. And basically, for the most part, I put some voltages there. If you're in Southern California, Edison territory, there is 4 distribution voltages, 4, 12, 16, and 18 kV. So basically what you get is 18 kV between these 2 points. Yes?
I always wanted to ask why it's shaped like this, like it's ice cream cup. You know, like the high voltage side, because it's shaped
Oh, you mean like this and not like this?
like the white part. You know,
Why are the tips like
You mean the insulators?
Yeah, yeah.
Why is it that they're
they're like conical rings?
like this?
Like ice cream.
Yeah, because what you want, so here's one of the issues, right? The tank itself is metal, right? Let me point it out. That's a pretty good question, by the way. This here is metal, right? This is non-carrying current metal, meaning, and obviously I don't want you to do that, but you can put your hand on it, and you're not gonna get shot, right? Now, think about this. This metal piece right here, that's light, right? So the insulator right here, basically what it's doing is it's insulating the can or the non-conductive parts from the conductive part. Why is it shaped like this? There's a lot of reasons, but one of the main reasons is what you want to do is you want to prevent current to start leaking into the insulator. So when water comes, if it's like this, it's much easier for water to go this way, especially when the insulators are really small. So water, what you don't want is this. So if I have the insulators like this, I'm exaggerating, but the water can go like this
That drips.
and then break. What you don't want is water to be continuous, because if water is continuous, there's a light part.
It's a short.
What exactly? Then you can flash it over, right? So that's why you know, insulators, especially insulators, there's a lot that goes into it. It looks just like a piece of this is ceramic, right? There's a lot of polymer that we use now in the industry, but these are mostly ceramic. These ones are not as expensive, and as the design is not as complex as the one that I'll show you in a minute. But that's the idea. The idea is to insulate the light parts from the non-light, right? And a lot of times you want these little skirts so that you can prevent from anything to build up and be continuous between the metal, because current is going to try to fight any metallic.
So why make the casing metallic in the first place?
Because remember, they get really hot.
Okay.
You have oil in there, so you want to use metal. I mean, what else can you use? Plastic? I don't think so, right?
Well,
So-
that heat and dissipate heat faster.
That's the other thing, and we'll talk about the cooling. And basically, this transformers, the single-phase oil transformers, the main cooling on the ones that you see up on the poles is the oil. But obviously, having metal helps because you use the metal as a heat dissipator, right? And the idea is that the oil goes to the wall, and there's ambient, just the breeze, right? And it's cooling it, right? So the more breeze you have, the better too, right?
It's like the old school
So
air
convection.
cool engines. They just use big chunk of metal.
It's like convection cooling.
I'll show you some of that as well.
Oh.
Here, there is heat, but we're not dealing with massive amounts of heat, but we're still dealing with heat. So you still have to do some cooling. Cooling is done by using oil. Now, the other thing I was going to tell you, probably the most recent developments in cooling for these small transformers, not for large ones, for small transformers, what we call, and you can Google that one too, it's called FR3, is a type of oil. It's an ester fluid that we call it. So the ester fluid, different from the organic or the oil that we have been using for the last, I don't know, 100 or so years, it has a much higher boiling point. So you can heat up the oil at a very, very high temperature, and you're not gonna have a flash internally, like, ignition. We used to make the jokes. What is the transformer replacing program by utilities? Meaning, when do the utilities decide to replace distribution transformers?
When they explode.
When they blow up. That's exactly right. When they blow up, that's when you change the transformer. So what is the challenge that we have, especially now, is that you have a transformer that blows up. It expels oil and flames, of course, very, very hot oil. you can ignite a fire, right? So that's why utilities now, especially in the state of California, are starting to push for ester fluid. Southern California Edison as an example, and PG&E and San Diego Gas and Electric, especially in high fire areas, they have gone as far as going proactively taking transformers, old transformers, with the conventional oil and replacing them with FR3 or ester fluid. So that's probably the latest and greatest, but even the process, the manufacturing process is very cookie cutter. You build one transformer, just to give you an example, the guys working in any of the utilities, they responsible for transformers, for pole-mounted transformers, they probably go to the factory maybe every 2 years to do a quick inspection of the quality and see if things are running fine. That's it, because they build them on batches. And I mean, if you go to the yards with PG&E and FUS utilities, you'll find tons and tons and tons of transformers because they, you always have transformers failing, especially in the summer. The summer is pretty bad. So, like I said, yes, there's some sort of design that you need to work on. There is some sort of standards that need to be followed, but they're fairly generic, meaning one design probably covers, a couple of designs covers all the electric utilities in the US, or if not most of them, so there's not a lot to it. So that's, like I said, they're almost exclusively oil-cooled transformers. And the oil doesn't move. There is a new dry-type transformer that Siemens has. They've been pushing for a while, but utilities are still not comfortable with it. So, and by the way, it's a pretty small footprint, probably a little lighter than this one, which for utilities is a plus too, right? Because remember, the weight is important because your pulse, right? You got to make sure that your pulse can hold the load. So there's a lot of that stuff that goes with it. This example that I gave you, and you probably will see it if you ever see 3 of these cylinders. They're basically a 3-phase. It's a 3-phase feed. It's a 3-phase transformer. So if you go to near industrial facilities, there's a lot of them right here. As a matter of fact, you see all those the warehouses. You probably will see those type of arrangements where you have 3 transformers. Each one of them is 1 phase. And we'll talk about that, how they're connected and all that. But for the most part, residential areas, except here a couple you probably have I think this one is a fan mounted, but that's what you will see. You can feed on average 5-6 customers per transformer. More or less you would take. But as I said, there's not much to it. There's a core, there's a winding, insulators, and oil, and that's it. 3-phase pile-mounted transformers. This still distribution transformers, meaning you're taking 12, 16, 18 kV, and stepping it down to 120, 208, 480, 377. But there's some areas where you cannot put transformers overhead. You cannot put lines overhead. Everything has to be undergrounded, right? As an example, city of Irvine is the one that comes to mind. If you go to Irvine, you see some transmission lines, but you never see distribution feeders.
New York.
Hmm?
New York's always underground.
New York? Yes. New York, the city of New York is heavily undergrounded. And they have a lot of problems in New York, and because it's a pretty old network. But these ones, you see them around probably. You see these green boxes just sitting. I think there's a couple here if you go around. Those are what we call distribution pile-mounted transformers. These are not single-phase. It's not economically feasible to build single-phase pile-mounted transformers, so they're mostly built as a 3-phase. And obviously, 3-phase, you feed more customers with one transformer than if you have a pole-mounted, right? So it's a higher capacity. These ones are usually 1 MVA 2 MVA. They're now pushing as a matter of fact, there's another push from the Department of Energy to go up to 5 MVA transformers, pan mounted for, and the idea is efficiency, right? To reduce footprint, to manage efficiency better. And there's new materials that are coming up for this pan mounted transformers. But you see this on residential areas. They're everywhere. They're what we call a front, dead front, meaning nothing there is light, right? That being said, same thing I always tell people, do not. I mean, they're out in the street, right? You can touch them, right? Nobody's gonna tell them. I don't touch this kind of stuff. You never know. It only takes one little problem for the structure to become energized. How often? Maybe almost never, but do you want to be the 0.01%? So my advice is if anybody sees anybody touching, just say, I wouldn't touch that, right? But the reason why, that one is a smaller one, it's a 45 kVA, but the reason, once again, we call it dead front is because the front of it, there's no light parts, okay? And then you can see those red things, there's these things that look like elbows, and that's what they put the faces. The feet is usually from the bottom, they're usually bottom feet. So those cables obviously are cables that are buried. There's another one over there with a meter. So those are, once again, pan mounted. These ones right here are what we call underground distribution. They're
I'm just curious, how modular is this type of system? Like, if something were to go bad on one of them, is it easy to remove and put back, or do you have to tear things out?
you have to take the whole thing out.
Oh man.
Yeah, you have to. What's easy to remove is the cables coming in.
Yeah.
You can pull the elbows, right? But the structure itself, the transformer itself, you got to pull it out and move it. Which is it's not that hard, right, to do it. But obviously there's work. Right, there's work. The pad is already designed to bolt it, so they're bolted to the ground. There's a little platform that they use, but they're replaceable. And as I said, obviously the lines they look like little elbows. They just pull the elbows.
But the lines themselves that run on the ground are huge.
They're probably about this big.
Yeah.
Yeah. They're pretty big lines in comparison to the conductor that you see on the top for the same opacity, right? Because once again, in the air, if you have an overhead line, it's outside, right? You have all kinds of stuff there, like you have wind, right? You have that they're out in air, so it's easier to cool them off. When you bury the line, they're buried, so it's like you put something in a box, right? You gotta find a way to dissipate heat. So in order to dissipate heat, you just increase the size of the conductor. That's basically what it is. You gotta increase the surface area. This one's right here. I was trying to find it's hard to see this one. These are in volts, so they're pretty common too. Those are very unique designs. They're called submersible transformers. The reason what we call them submersible is because water can get in there. They can be completely submerged in water, and they should be running. So, as a matter of fact, this is one of the things that I've been working with Southern Cal Edison right now. They only have one company that provides those type of transformers. I'm trying to see if we can get a second one. But they're very, very special design and stainless steel. They use stainless steel for the and it looks very much like a pole mounted transformer. It's that big cylinder, but obviously more expensive, right? As far as cost, cheap, halfway cheap, and not too cheap, meaning the price increases from the pole mounted, with this being the more expensive for distribution transformers. But you guys can see there's a lot more work that goes with it too, right? There's a lot of civil work. The other one, you just put a pad, the other one, they hang it. This one, no, you actually got to build a vault with with, what do you call it, raceways, and there's a lot of stuff that goes with it, so, it's not very cheap. But some cities, they won't allow that, and they won't allow the one on the pole. They want everything completely buried. I don't want to see anything. So it depends on the city's ordinance. Oh, yes, this one's, I forgot to mention, these ones are dry type. There's no oil on them. The only way this cool is with air, and ambient air, nothing, no forced air, no fans, no nothing. And hence, the casing is a lot larger because you need more surface area to cool them off. The ones that are the ones that are on the underground or the submersible transformers, those are oil filled transformers. So because cooling is not as easy. All right. So we go from distribution to substation transformers. So substation transformers, obviously size-wise, much larger. Cost a lot more. Design, boy, to get a transformer designed right now, just to give you an example, most companies now that build large transformers, and I'm talking very large transformers, 100 MVA to 250 MVA. And I'm talking about, except for Chinese companies, but for the most part, European companies, South American companies that build large transformers, Mexico, you cannot get a transformer right now, probably until 20, if you order it today, maybe 2028, 2029. It takes a long, long time from the time you order to the time you actually, the utility gets here in their hand, because the process of designing is long, manufacturing is long, it takes a very long time. So obviously, a lot more expensive. That's a three-phase transformer, the one right on top. You can see phases A, B, and C. And then on this side right here, you can see the high and the low side. How do you know which one's the low side and which is the high side?
The smaller one is the low side. Huh?
Say it again.
The size of the pole determines if it's a high or low side.
Right. So the longer the insulator and the longer the longer the spacing between the phases is the higher side, right? Because the higher the voltage, the more space you need, right? If you bring them too close together, you're gonna have flashover, right? So it's a minimum clearance that you gotta have between phases, between the two potentials, without having to ionize the air and have a flashover between phases. But remember, there are two different potentials. If it's a 500 kV, it's a 500 line-to-line RMS. The low side, obviously, the smaller the insulators, but oftentimes the high side has thinner conductors, and the low side has much larger conductors, meaning surface-wise. Because remember, you're transferring the same amount of energy, so you increase the voltage, you gotta decrease the current, and vice versa. So when you decrease the voltage, the current goes up, so your conductors have to be a little larger. But just from looking at them, how can you tell which one is the high side, which one is the low side? You can see just by the size of the length of the insulator. We'll take a look at some insulators in more detail. There is such a thing as an underground three-phase large transformers. That picture there, I don't know, I never seen one in the US. That doesn't mean that doesn't exist. Somebody gave me that picture. This is a transformer. This is a Japanese company. I think it's TEPCO Electric. Somebody was talking about one time, and I asked if I can get the picture because I have never seen one. I was like, whoa, that thing is massive and is in a bowl. Somebody asked the question when we were talking about this. You asked me, hey, what do you do when it fails? Like, is it easy to? Can you imagine a transformer like this failing inside the bowl and having to change it? I mean, it's a big ordeal to do that. That transformer, I think, is Hitachi, the company who designed the transformer. And the guy who was talking about it said they asked the Japanese engineers, like, so what is the what is the procedure, what is the process to change the transformer if it fails? The engineers, the designer said, transformer doesn't fail. What do you mean, transformer doesn't fail? Meaning, we put a lot of money into this transformer, and the design is that the design is so robust, it's not going to fail. That's how confident I think they are, but you can see it, right? I mean, and you can see the people, like, in comparison to the actual the transformer tank. It is a pretty big device. Like I said, I never seen one in the U.S. I don't know, at least in the Western U.S. I don't know there's one. They could be, but I came across any. The other thing is single phase transformer. Sometimes transformer, the NVA becomes so large that you cannot have all three phases of one tank. It will be way too big. So what we do is we break it into three pieces and make phase A, B, and C separate. And you can see this one right here is a bank. You can see 1, 2, this is a picture, it was under construction. The substation is called Whirlwind. If you guys ever drive in, it's in the Mojave Desert, city of Mojave, I'm sorry. And that's when Edison was trying to pull a lot of wind energy from that area. They built this station, that's what they call Whirlwind. It's a very large station, but somebody gave me this pictures, and you can see it wasn't finished. They were under construction. So phases A, B, and I think phase C was right here somewhere. Once again, if you were to put all three together, the tank would be as big as this room. Impossible. How do you move it, right? There's no way to move it. So the only way to achieve, this one right here, you can see it. I think I took this picture. Phases A, B, and C. So that's one transformer, okay? Probably 250 MVA, that's a very common size for this transformers. Now, we'll get into more details on this as well.
Being underground,
Say that again?
being underground is another benefit to prevent terrorism.
The underground has a lot of benefits. A lot of benefits. I mean, just the simple fact that you don't see the equipment, right? You don't see these big structures next to your house. The other thing is the chances of somebody hitting the structure or doing something is a lot less, right? Because they're buried, right? It's nothing, right? Nothing like, there's no cars, no trucks, nothing that can hit them. The other thing, I think I talked to you guys about is rodents. Rodents is a big problem for utilities, right? So if everything is exposed, it's exposed, right? It's exposed to the elements, exposed to nature, exposed to incidents. The one thing that is still happening, especially in rural areas, is people use the insulators as target practice. It's very common. People using insulators as target practice. And by the way, if you know anybody who ever does that, just tell them that you go to jail for a long time.
Like target practice is like shooting?
Yes, shooting, target practice is shooting. They like insulators for that. So if you have it buried, like, that's not a problem, right? But it's been a problem. More than at least, because these substations are really well protected. If you ever go to this big station, there's a wall and there's another wall in between the wall. There's just no way to get in. Somehow people have still gotten to them. But it's a federal crime because anything above 100 kilovolts is a federal jurisdiction. It's not the police you're going to be dealing with, it's FBI, because it's considered federal property. So I was, if you work for Southern Cal Edison, I will highly recommend that you find out if they can give you a tour of the Chino underground facility, which is not that far from here. It's only like 6 miles. It's right up to 71. That's a very good example of bearing ultra high voltage. That's a 500 kilovolt line. And you'll see this things that look like transformers. They look exactly like transformers. And you look at them, but there's only one insulator, and you go, oh, I see a primary, where's the secondary? Those are reactors. Because the underground cable produces a lot of bars, so you need reactors to absorb bars because of the capacitance of those lines. But the design is very much the same. Cooling, we talked about cooling. So on large transformers, there is different type in which you can cool the transformer. You can use oil, natural oil, and air natural cooling. What does that mean? The oil is in the tank, standing, it doesn't move, and the only air that is helping you cool the transformers is the air. There's no pumps, nothing. You can have a transformer that has oil natural, meaning oil just sitting there, but then you can have force cooling. In other words, you can have fans on top of it, okay? And then you can have oil force and air force. In other words, you can have the tank, and the tank has a pump, and it's circulating oil to these radiators, and then you have fans blowing on the oil. Kind of the same concept in your car, right? Where you have a radiator, and the water is cooling the engine going out, it's blowing, and then you have the big fan on your car. It's a very similar concept. Some companies don't like this because the maintenance, there's a lot of maintenance. Now you gotta worry about a fan, which is a motor. You have a DC motor on the transformer, and again, that becomes another failure mode on the transformer. So I believe Edison moved away from that. I don't know how long ago, but they moved away from pumps. Yes, sir.
Are there any transformers that use like Peltier coolers, anything like that?
That use of what, sir?
Like Peltier cooling?
Oh,
Like
sorry.
it's like phase exchange cooling, so they heat up one side and the other side gets really cold.
Oh, I never heard of that.
No, okay.
I never heard of that. That's a good one. We should Google it. Anyway, so but that's and when you get a transformer, the transformer is rated for those different things. For instance, if you say, oh, it's just say you say I have a 100 MVA that I want to push from the primary to the secondary, but if I turn on the fans, I can push 106 or 110 or 120. If I turn on the fans and I turn on the pump, then I can push 130 MVA. I'm just saying, depending on how much cooling you're providing, you can increase the transfer capacity of the transformer. So once you get out there, you're gonna hear this terminology, ONAM, ONAF, OAF. That's, like I said, those are three different types of cooling transformers. The oil is just natural oil. This, by the way, there has been questions about using it for three. Some companies like some PG&E are saying to us, big transformer manufacturers, to use ester fluid. So what you have, as I said, you have much higher boiling point on the oil, so you can push more power through it without having to worry about the oil getting to the point where you
And it's not conductive.
it's not so much the conductivity, is that you can get it to a point that you heat the oil so much that you can destroy the properties of the oil. Okay, and then then you can have other problems. There's a lot of other problems, and then you get damage. Yeah. So keeping the transformer at a normal temperature is key. Every time that you heat up the transformer with its normal operating or rated temperature, you're eating up the life.
Does this oil usually get like drained out and replaced?
The oil can get drained out and replaced. Yes, there is such a thing. As a matter of fact, oh man, I have those pictures. I should put them here. I think it was about 3 years ago. I went to a Siemens factory, and it was a synchronous generator factory, but they also had a maintenance facility, and the maintenance facility had these trucks, big trucks that they drive around the U.S. to do it precisely that. So basically what they do, they bring the truck, they hook up the truck and they drain the oil is damaged. There is on very large transformers, especially now, they have a lot of, they call it DGA, dissolved gas analysis, where they're constantly analyzing the oil and the quality of the oil. Problem is that if you get moisture in the oil, or if oil starts breaking down, then you can have a flashover internally and the transformer is done. So yes, the answer is yes. So they have this big trucks, big trucks with all these pipes, and basically what they do is they suck all of the oil, and in some cases, you can refilter or recycle the oil. You can filter it, and some impurities you can clean them up, or you can just completely change the oil. But yeah, there's such a thing. Let's see. So that's cooling, and I have a better slides for this, but just kind of give you an idea. Some of the main parts, obviously the bushes, the oil reservoir, basically that's, if you were to have a leak of oil, you want to make sure that you have enough oil so that the tank is always full. The other thing is that what happens when oil heats up? It expands, right? So the reservoir is basically doing that, it's serving as a place where the overflow of the oil can go, right? So that's that big tank over there. Always the radiators, fans, you can see and I have much better pictures than that on your winding and cord and the tank. For the most part, in very large transformers, especially, there are only a few factories that will build a tank in a central facility. They want to keep a very good control of the entire manufacturing process, so everything is done inside the same, basically the same campus, I would say, right? So, but there are companies, that will have the manufacturing of the tank in one country, and then the light part, we call light everything but the tank, so the light part in a different place. But for the most part, like I said, especially those Korean companies like Hyundai, Haito, they do all of it in just one building. But just give you some pictures there.
When they do a big transformer, do they all usually do a tiny version of it first before they scale it up?
No, I see companies do this. They use what do you call those printers? 3D printers, just to make little, but not for design. The design is a very how do I say it, long process. It takes a few months to get through a transformer design review. And it's prints. You have prints, your printed documents this big. It's a lot of work to get to that. Core types. There's two core types that you probably come across when it comes to transformers. There is the core and shell type. The difference is, if you can see here, obviously the gray part is your core, or your what do you say it, your iron, called the iron part, and then what you see here, these yellow things are the windings. So you can see on the core type, you have this leg and this leg, and the windings are wrapped around these two legs. Whereas a shell type, there's nothing on this outside legs. This is depending on the company, depending on the utility. Some utilities prefer core type. I'm sorry. I wrote it wrong. It's my bad. This should be shell type. Shell type and core type. No, I got it. So why will you go one versus the other? There's a lot of reasons. These ones right here are more robust. If you can see this one, you can think of the winding hanging out of the cord, right? So especially when you have faults, then you have this very, very high tangential forces that are developed when you have a fault. So if you have a shell type, you have these two outside limbs or legs that are protecting the winding. Whereas this one is, you can say, exposed, right? So this could be more expensive than that, right? But this is more robust. Again, it depends on the utility. Some utilities will just buy core types, some utilities just buy shell type. So manufacturers prefer to use shell type, and so manufacturers would prefer that. They will sell you. That's a selling point that they have sometimes to tell you, hey, we specialize in this type of design. But again, there's a lot of things that pros and cons with each one.
So it's right? Left is core, right is shell.
Right. Right. Let me see. Here, I gave you some pictures of shell and core types that I found. Transportation is a big deal. That's what I was telling you. I mean, if I want to do a 3-phase 250 MVA transformer, the tank will be this big as this room. How in the heck do you get that from Europe to the US? Or from Japan to the US, or from Korea to the US, right? How do you get them on the road without breaking the road, right? So there is a limit on the weight as well that the cities will. Have you ever seen a transformer being moved? Oh, you seen it?
Yeah.
Oh, cool. They do it like in the middle of the night on a weekend where nobody. Is a big
They shut
deal.
everything down.
I'm sorry?
They shut the whole road down.
They show the whole road. That's right. They shut the whole road, and it takes a long, long time. But this plane, I was watching a documentary. This plane is, it used to be part of the Soviet Air Force.
The F-zone something.
I forget the name of that plane, but it's
Like
ginormous.
6 engine on one side.
Right, but then when the Soviet Union broke down, was broken, oh my God, what's the name of the country?
Russia.
No, not Russia.
Ukraine.
Huh?
Ended up in Ukraine.
Ukraine, I'm sorry.
Yeah,
So bad, I see the colors of the flag and I can't even remember. The Ukraine kept these planes. They kept the fleet, and that's what they use it for, not just transform, but to move large equipment. Transformers being one of them.
It got shut down too.
Say that again?
It got shut down.
It probably got shut down, yeah, I wouldn't be surprised.
Shut.
They don't have it anymore, is that what you're telling me?
During the war,
Uh-huh.
I think someone shut it down. So they
Oh,
don't have it.
they don't have them anymore. It used to be, the companies still use that, for the most part, transformers, especially very large transformers are through the ocean, right? And that's another big thing for companies that build large transformers. They want to be next to a big river so that they can push them out. But that one picture too, somebody gave me that picture too. This one right here is pretty old. I might have been in the 1990s when that happened. Anyways, utilities usually have spare transformers. So like a substation here, especially like a very large 500 to 230 kV station will have phases A, B, and C, and they have a fourth spare transformer just in case one fails. They just move it. This one right here, the story was that there was a failure of a transformer in Arizona, and this transformer was being borrowed by APS from SCE. So you can see that they were moving it from an SCE facility to Arizona. The point is that, as I said, one blows up. It's not that easy to get one. To the point that during the Obama administration, they created a program called STEP, and don't ask me what it stands for. Basically, what STEP did is they asked all the utilities in different regions to pull together money and buy spare transformers, and they're hiding. Nobody knows where they are. if there's a terrorist attack, or especially, it's mostly for terrorist attack, and a substation gets, damaged, they have transformers in some places throughout the U.S. Where utilities can go and get. The challenge with that was the biggest challenge with this, the design. Every utility has their own design, but those transformers are mostly for emergency purposes only. Eventually, right, the utility will buy their own transformer, but here's another one. It's hard to see, but I don't remember where I got this one. That one I do remember. This one I don't remember. So moving this pieces of equipment, like I said, it does have a bunch of things. Like it has accelerators. It has this sensors that if the transformer tilts too much while they're moving, right? The utility will say no. Okay, right? Because you move it, you can shift the cord or the light parts inside the tank. So it's a, like I said, that's what they pay a lot. I found this really cool slides, a video. I'm gonna give you the video so you can watch it. Amazing, whoever did this, like, wow. I just kind of give you some ideas. So transformers, just in general, right? Three-phase transformers, and they put this picture of somebody just to give you an idea of the size. This is distribution flat-mounted transformers. Very European looking, by the way. We don't use this kind of stand in the US. This is a light. It has light wires right here. Remember the green boxes that I showed you? There's nothing exposed. Europeans use this, especially Eastern Europe. They use this design a lot. Obviously, very large substation transformer, pole mounted. And then we have current and potential transformers, which is not what we're going to be talking in this class, but there exists, right? Those are transformers that are used to step up and down voltages so that can be used for measurements, right? So relay control equipment is connected to current and potential transformers. Yes, sir.
I know you were talking about these three-phase, and you were saying that they usually don't have very high losses, but how can they generate so much heat? Is the heat considered part of the losses?
Yes, how we measure losses. As a matter of fact, and we're going to talk about this. When we talk about transformer models. So in the transformer model, you have an R1 and R2, R primary and R secondary. Those are the resistances in the model that are accounting for those losses, right? If you get like a pole mounted or a plant mounted transformer, when the manufacturer gives you the information, they give you the ohms values, right? They tell this is the R, this is the X. When you're talking about these very large transformers, what the manufacturer gives you is the kilowatt. You will figure out the R. I'll give you the kilowatt because that's how they account for the losses is kilowatts. Well, in both cases, it's kilowatts, right? What I'm trying to say is that for very large transformer, losses are given to the owner of the equipment in kW. So when you go to a transformer report, it says 250 MVA, primary losses, blah, 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 kW, right? Again, if you're talking about 250 MVA, right?
I'd say kilowatts, it's not that much.
It's not that much.
So I guess, and if that's how much it takes to cool it, you can think about how much energy it's actually.
Thank you.
Right.
Thank you.
So
it's a lot of energy. It's an insane amount of energy that you're pushing through this.
So the cooling is a little fraction of what it actually.
Oh, yes.
Got it.
Oh, yes. Oh, yes. Right, right. The design itself is kind of, is very interesting. So here is the primary and secondary phases A, B, and C. And I'll show you, there's a picture that breaks it down. So they're basically cylinders on the winding here, and there's a cylinder. The winding here, there's another cylinder. So the primary and the secondary are like right in between each other. They're like pancake. So that's, for very large transformer, that's the core design. It doesn't matter whether it's Hitachi, Mitsubishi, Smith, Hyundai. The design is very similar. There's some little things, little tiny things that some companies will say, we do our windings this way. And that's where transformers are so special and much better than company X, Y, and Z, right? They all have little things on the design that makes them, how do I say, differentiate from other. But the concept, the way the main design is pretty much the same. The company, and I'm not saying this just because, I mean, the company that I work with is called Smith. Smith is considered like, I don't know, the Rolls Royce of transformers. They're very expensive. But the company not only has been around for almost 120 years, they've been around for a long time. Their designs are flawless, and they have some little things inside on the core, how they design and package the core that is proprietary to them. They own the design, so they sell that, right? So they're very heavy, and when I mean very heavy, they use a lot of copper and they use a lot of iron. They don't cut corners. But obviously, if you buy a Smith transformer, it's going to cost you a little more than if you buy a transformer from China. Chinese transformers are cheap, but they can last you forever. So there's a lot to be said about that. But the main design, and doesn't change much.
You're saying the primary and second is like trying to put two springs together.
Yeah, okay, so I'm showing you right here. This right here is the high side winding. And this right, so you need more turns, right? So transformers 230 to 500, you need 500 turns, 230 turns, right? So the other thing is the way that they're designed, this right here is just mostly cooling purposes. And there's a lot of things that in the winding, there's a lot of spacers, and for the most part, that's what they're trying to achieve. They're trying to reduce the heat losses as much as possible. So, so here's, like I said, here's the high side winding, and here's the low side winding. This right here, which was on this, that's a very important piece of a large transformer, which is this device right here is called a tap changer. Basically what you do is, we'll talk about that, but say for instance you have a transformer winding, and you can tap the winding. So here you get the full voltage right from this point to this point, but if you want to, you can actually increase it, right? You can have a plus 5%, minus 5%. What I mean by that is you can have this device that is tapping the winding on different spots, right? So instead of taking 500 turns, I'm just gonna take 450 turns. So it moves the connection to a different spot on the winding. Or if I want to increase, I go from 500, I don't know, to 510 turns. So that's what this thing here does. It looks, it's like a bunch of little discs with these things, and basically what they're doing, they're tapping, and that is their automatic tap changer. So the transformer is being set to function between plus minus certain voltage, and when the voltage is depressed, the tap changer goes. There's a motor and it increases the voltage or decreases the voltage by the percent that the transformer is being designed. Believe it or not, that is one piece that the transformer manufacturers don't manufacture. They buy the company that is by far the best company is called Reihausen. It's a company in Germany. There's a town Reihausen, and that's what most transformer manufacturers buy that one little piece from, which is
So that's slowly the only the active control that you can have.
Say that again.
That's the only active control you can have with this.
You can say yes, yes, that's the only active piece. That's the piece that actually moves unless you have pumps, right? But yes. And I'm talking large transformers. Small transformers don't have tap changers. Too expensive to have a tap changer. tap changers, this one, I think I have a picture of the external one. In some cases, some utilities, their designs, they don't allow the tap changer to be inside the tank where the windings are. They want to have an external tank just for the tap changer. So they call it an external tap, right? They want a whole different, because once again, it's failure points, right? If the tap changer fails, it's gonna damage the entire transformer. So they wanna reduce the failure points, that's basically what it is. Tank, the tank is a very important piece. Actually, no, I have another picture. So, as I mentioned to you, this right here, in some cases, some companies, they want to manufacture everything in the same place. Remember those little transformers that I showed you, the pole mounted? And the factory building the cylinders is 3 states away. They just assemble. This is not just a simple assemble. So the more you can contain the design in the one facility, the better chances that even the customer, taking your design, because they see all that. Just moving something, every time you move something, you're exposing this. But the tank, like I said, it's a very critical piece, and it's 100% sealed, vacuum sealed, so that they can maintain the quality of the light bars and the oil inside. And they're pretty big pieces. Now the other thing, we're talking about insulators. This insulators are so much sophisticated than the ones that I show you. Those on the little transformers, they're just a ceramic disc, nothing in it, just a conductor inside, a ceramic disc and a terminal. This one's right here, they're actually oil filled. I mean, you can see there's a little window. It's hard to see. I'll give you the slide so you can see it. But there's like a little window right there where they're monitoring the oil, the level of the oil on the insulator itself. And it's not inside the insulators, because that's where you put the conductor coming from the transmission line or the distribution line, and that goes into the winding, right? That inside that insulator is not a conductor. In some cases, they use this they look like, how do I say it? Something like this. Like if I take this paper, it's like this, copper sheets, right? And one thing is to reduce capacitance. That's one thing. It also reduce what do you call eddy currents. There's a lot of things, that because you're talking about through that insulator, that's where all the energy is flowing. So it's a lot of energy. So they're, like I said, they're usually oil cooled. Oh, by the way, I said that the tap changer is the one piece that the transformer manufacturers don't manufacture. That's another one. They don't manufacture that. They buy it from companies. But those companies are very well established. As a matter of fact, the current transformers, to make sure current going in and out, in some cases it's built into the insulator. So there is a donut, it looks like a donut that is a core, it's a current transformer built in there. So it's sort of built into the transformer insulator. Let's see. This picture was really cool because it just shows all the light parts. We call this light parts. This is there, and then we can see oil. The oil is filled all the way to the top. And oh yeah, the one piece that I was going to tell you is this right here. This process, the manufacturing process of it, and there is a phase where they dry it because you want to extract every molecule of moisture that can be trapped you want to extract it because the last thing you want inside the transformer is any type of water particle. Any moisture, once the transformer is energized in the oil, it can cause these little bubbles to develop, and they cannot necessarily have to be large bubbles, they're tiny bubbles, and it can just damage the transformer. You can have a flashover. So the baking part, it is like I said, it's a long process. There was a story. I was talking to somebody the other day. I was working on. I wasn't working. Let me take that back because I was not working. I was not the engineer. I was the manager of the apparatus group. And there's an engineer, Edison, working on transformer. He asked me, "Hey, Juan, you want to come with me? We're going to go and do the design review at this factory in Memphis, and it's a new factory for Mitsubishi." He said, "I just want to take you. Just want you to go with me so you can see what they do." All right, I went with him. So we were doing the testing, and as we transformer that was the trick. It was about going and do what they call impulse tests, where you apply very high voltage impulses on the insulators to see how the transformer will deal with lightning or high switching transients. And the transformer didn't pass. And transformer didn't pass. And that's a big deal because transformer needs to be delivered. If the transformer is not delivered, you're not transforming energy. If you're not transforming energy, you're not making money. So there is a date where the transformer should be energized, and that date must be right on that day. So long story short, it took about a year to fix the transformer, and it was a painful year because I was the manager of the group, and operations they were all over me at that time. Like, you guys got to do this. I mean, I don't know what you guys got. We're losing a lot of money. What the heck happened? Who messed up on this design? Right? So it turns out that this was a really nice factory, big factory that Mitsubishi had opened. We were transformer number 2. They left the transformer, this light parts, outside for a day, one extra day that they should have been out, and instead it collected moisture, and that's what was showing up. When you do the lightning impulse, those little bubbles show up on the test. So they have to take the oil out, take all the lights part out, dry them up again. So it was a big deal. So that's what I'm trying to tell you, that it is a very, very meticulous process. And companies can lose millions of dollars. This is transformer just completed. This is another picture I wanted to show you. So this one, of course, has the fans, the radiators. I don't know, I didn't see a pump here. Maybe in this joint they didn't have it. And then the controls. Here's all the controls. And in this type of transformer, as I said, they have all the tap changers are internally built. They're inside the tank. Just give you an idea. This is the factory. This is the Smith factory. You can see where they're building here's part of the core and the winding. Obviously, what they do is they bring another, it looks like another E, and they put it on top, and they gotta precisely match the one on top and the one on the bottom. You can see the conductors here coming out. Those are the conductors coming out from the cylinder that is inside, which is the low voltage winding. Let's see. You can kind of see the core lamination. You see it right here. And here, when you see it, it looks like, oh, there are sheets of, how do you call it, iron, right? And just by looking at the picture, it looks like they're this thick. Actually, they're not. The thickness of it is, I think it's less, 1/10 of this page. That's how thin they are. And I think, I forgot that picture. I put my finger on one of them just to show people like how thin those sheets are, right? So you have this long sheets of iron, and they just stack on each other. And when we'll talk about the flux and how the flux is managed inside the core, we'll go through those concepts. I'm gonna I'm gonna remind you of that, the importance of making the core so precise that you don't even have the little laminations, one larger than the other, you gotta be precise. If you put your hand like this, you don't feel it. Because if there's one, you're gonna cut yourself. They're extremely, extremely sharp. Remember I was talking about this when we're talking about electromagnetic concept, and I said, hey, this is some sort of iron with some sort of impurities. Remember I talked about that? And I said they have silicon, so those sheets they use those impurities to reduce what?
Eddy current.
Eddy currents, right? So, and the thinner the sheets, the lower the eddy currents, the lower the losses. Let me see what oh yeah, I do have this. I should have waited, but you can see the sharp edges right here. Once the core is completely finished, they make sure that this sharp edges, if you look from the top, you just see one dot. They have to be precisely, otherwise you have issues with the flux not being uniform. So you gotta, in order to maintain the flux on the core uniform, the shape, the geometry of it must be very, very precise. And there's a radiator that they were probably moving around. I have a picture of one of the tanks, and I went inside the tank to take a picture, and I couldn't find it. I don't know what I did with it. Finished product. Let me see. Is this the one? Oh, it's hard to see. This one right here. This one right here. This had an external tap changer, but they have not assembled that yet. So I don't know. I forgot that picture too. This one was a 150 MVA. Actually, it was for the US. I cannot remember what utility, but one of the utilities in the East. And then you can see this one actually, it has the radiators separate. And the reason why they have separate is because right here they're just testing the transformer, so they're not there yet with the full assembly. So they just have these radiators, and they're starting to put up oil and flow the oil. They don't energize it, but they also want to test the controls for those fans as well. So, but they're separated. Eventually, they will bring it through here. This right here is a training transformer. It's right outside this, where this transformer was. This is where they train the technicians and utility people that do maintenance on transformer. They bring them there, and they do all kinds of stuff in there, but they just for testing purposes. This one is the same transformer from a different angle. Oh, this one you can see the radiators, the tank. This is, oh yeah, I remember this one right here. This is a single phase transformer. It's just one phase. This is a 765 kV. Those companies called AEP. It's a company in Ohio. That's where these transformers were going. They were ready to go on the testing. They do test that I told you, which is the input test. That's guy from Edison, my boss in there. Here's right outside the factory. You can see there's two transformers right here that they're about to ship out. Do you see any insulators? There's a word called undress. They undress them. They take all the insulators off. They seal the tank, and then they ship this thing separate. And then once that they arrive to the substation, they bring the rest of the parts and they assemble that, moving the transformer with all those pieces. You're asking for trouble. I forgot the name of this truck. They had a name of that truck. And the river is right next to it. You drive like a few blocks and they have those bars, those shipping, big shipping containers, and they just put them in there and they make their way to South America, the US, Canada, wherever they're sending. This was a funny picture. I don't know why the angle is really weird. The one thing is that you get is when you go see this is the sheer size of it. If you walk in there, you go, holy moly, these things are ginormous. They're really, really big. And that's what I was telling you guys, designing one of these things. Right now, for 250 MVA, I'm gonna put that on like those single phase boxes. About 5 years, we have a project right now with SCE and LADWP. I think 2028, 2029, I think is when they're gonna be delivered. So it does take a long time. If you ever have the desire, the itch to work in this, and this is all you do transformers. It is a very, for engineers, I call it a very lucrative career because there's not a lot of people that we train in the industry. Actually, the Department of Energy was asking utilities to get more engineers training. They were even talking about a program sending engineers to work in the factories in Korea, Germany, Japan, because we're losing a lot of knowledge. As simple as it might sound, just iron and a bunch of wood, craft paper, copper, and it doesn't sound like it's a lot, but no, there's quite a lot. And the nice thing about it now is that there is more and more equipment and sensors that are starting to be developed to have what they call a real-time maintenance or real-time health of the transformer, especially transformers that they're such a big commodity. It costs a lot of money, and the utilities want to maximize their investment. Just to give you an idea, let me see, a full bank, say, guesstimate, but between 10 and 50 million dollars per, so for those 3 boxes. So it's a lot of money the utilities are putting up front. So the investment is pretty large. So I have only seen one incident, and it was actually a month after I joined Southern California Edison. Literally a month after I joined, there was a fire right off the 18, I think it is. If you're going on the 5, you go to Palmdale. There's a substation called Vincent. One of the transformers, one of the phases got on fire. Just one got on fire. And then that one spilled over, and spilled over. All 3 banks were completely gone. They're melted. Once they start burning, they're done. I just need a little bit of fire, and even the firefighters won't put water in it. It's just going until they completely melt, and they gotta do the cleanup. What Edison started doing after that, they put walls, retainer walls between transformer banks, so that if there is a fire, you contain the fire in that one leg. But as I said, if you ever have an opportunity to work, actually, I think next fall, I heard, I don't know if it's for sure, but I heard next fall, they're probably gonna be looking for a couple of engineers at Edison in the apparatus group. And if you get a job, you get a job. But if you get a job, and especially in these areas like transformer circuit breakers, and you learn this stuff and you master some of this stuff, I'm telling you, you can make a lot of money. And you can call your price. But, any questions? All right. So let's get into now the theory. I'll give you the slides. And if you have any questions about it, if you're interested, oh yes, I was gonna say this. Hyundai and Siemens just announced, which is not good for me, but just announced they're gonna be opening 2 new factories. One in Raleigh, North Carolina, which they already have one that they're expanding into, and then the other one, can't remember what state for Hyundai, they're gonna be looking for engineers. Gonna be a lot of engineers, but you have to move. That's the problem. If you're interested. All right, so power transformers. We said that power, or transformers in here, but power, transformers, operate on the principles of electromagnetic induction. By establishing a magnetic field, which induces currents from primary to secondary winding. A flux that aligns, and I think we talked about this when I was talking about the electromagnetic concept, aligns with a with the field, the magnetic field, and it is time varying, and this is key. This is the one reason why we can achieve the transformation, or we can induce a current from the primary to the secondary using the electromagnetic induction. If it is not time varying, then we will not be able to, and I'll explain it in more details in a bit. So you can think of a transformer core. This is your steel core, and obviously a winding, primary and secondary. Secondary. I'm going to say this is P in, and this is P out. And again, P is a function of voltage and current, right? We talked about that. So you have an I primary, and I secondary. Once you start pushing current through this winding, you're going to produce a field and a flux. We talked about that a little bit ago. You're gonna get a flux. We're just gonna put the average flux that follows the magnetic field. Okay, and we're gonna call this P, right? So magnetic flux lines. And I said that, right? When we were talking about the flux, I said, well, it's not one line, it's multiple lines of flux, but we actually combine them and we take the average flux when we're talking about the flux that is in the core. Now, the one nice thing is that remember when we're talking about flux lines, whether they're in some sort of material, depending on the quality of the material. Remember I said if you have plastic, can you establish can you put a filter? Can I take this marker and put a winding around it of copper, put a voltage source right here, push a current through the winding and establish a field? The answer is yes.
How strong it is?
But it's not as good, it's not as strong, and I cannot develop as many flux lines as I will do if I had a material that is really good in conducting, I'm going to say, or in allowing flux lines to develop, right? So air is the worst thing, right? Air doesn't conduct or doesn't allow for flux lines to travel very easily. So the reason why transformers in comparison to rotating machines are so much efficient because all the flux is confined in the core. If you have a rotating machine or a motor, generator, machine, basically what you're doing is you're cutting the cord, right? You can think of it this way. You can cut in the cord, you have a rotor, this winding goes here, but you have air. So the flux lines have to go through air, and remember, air is not really good in handling it, right? So that's why rotating machines are not as efficient as transformers, because the transformer, we don't have that problem. We assume that all of the flux lines are, once again, all confined within the core. Now, remember I was telling you about the spacing of the sheets of lamination transformer, the geometry, how precise it is. If it's not, then what you have, if you have, how do I say it? If the geometry is not as precise, but it results in the flux lines or the flux going into the air, escaping, especially on the corners or in the air, okay? And that's flux that you don't have, that you're losing, right? So they become losses. So they once again, maintaining the geometry very, very precise is helping you in making sure that the flux lines or the flux established is inside the core. I think I made the joke too to you guys that when I was in school, you do your senior design, and then a friend of mine and I decided to build a 1 kVA transformer. And we found a company in the city industry, I remember. This company, it's a small company, and they built small transformers. And we went there and we told them what we were doing, and they said, yeah, you guys want, we have a bunch of lamination, and we can give you a bunch of lamination and copper, already cut, of course, right? Yeah, you guys can build it. So they gave us a bunch of stuff. So I remember being in the hallway like this at school, doing windings, primary, secondary winding by hand. We put it together. We brought it to the lab, and we turned it on, and the thing started just going like this, and it was just going, it was jumping like this. We're doing it by hand, right? We didn't have the precision machinery to build it. We just kind of put it in the garage. Basically, the problem was, and the professor asked the question, and he was tough. This senior professor, and he said, turn that thing off, and I want you to explain me what happens, or I will pass you the class. Holy cow. He gave us, he's going through all the projects, and my friend, I'm like, holy cow, nope. Basically, that's what it was. What happened is that the geometry, how we have these laminations were not precisely aligned. They were like this. Like, you can see the edges. There's so much flux that was getting into, on the air, there was so much losses, and it resulted as vibrations, right? So there's a lot of things to be said about, but the idea, once again, is to maintain a very precise course so that your flux lines are within that. So, energy, 99%, I said, we're gonna study two types of models, an ideal and a non-ideal transformer model. On an ideal transformer model, the power you put in is the power you get out. If I put 100 MVA right here, I get 100 MVA on the other side. Is there such a thing? No, right? There's no way you can. I mean, you have losses. Remember we talked about the losses. You have copper losses, eddy currents, hysteresis losses. There's a lot of losses that you're going to incur, right? Maintaining the transformer, once again, design quality is helping you reduce your losses. The thinner the sheets, the less eddy currents, right? The better quality of the material that you're using, the better the hysteresis. So there's a lot to be set up on that and how you, once again, control these losses. But you're gonna say, I put so much MVA right here, and hopefully I'm gonna get just about the same amount. In reality, what utilities are shooting for, especially on very large transformers, I put 100 MVA right here, I should get here at close to 99.9%. And they do testing under different loading conditions, and they're monitoring that. And you know how if you go work for Edison, you work in the apparatus, you learn this. The way when they do the testing, the way they capture that information with the manufacturers in dollars. How much is it costing today in losses, right? So they have a table where they say, this is how much it's costing. So not being able to do that, once again, not being able to maintain the flux inside the core is a big deal. And the larger the transformer, the bigger the deal. All right, so the formula for flux as a function of time is equal to P of T is equal to P max sine omega T. Okay, so here, once again, you have a source right here. It's an AC source. Current is an AC current. Obviously, your flux is a sinusoid, okay? And it's represented with this equation. It changes, once again, with respect to time, where omega is equal to 2 pi f. And for us here in the US, it's 2 pi times 60, or 377 radians per second, right? That is omega. So that's the equation, once again, that is describing this flux on the core. Now, we start with this. Let's start with, we say that from Faraday's, Faraday's law, the EMF, electromagnetic force, we talk about this, or EMF, stands that E is equal to, there's a negative right here. Some equations will have the negative, some equations don't have it. I'll explain what this negative means, but it's E, or the electromotive force, or EMF, is equal to minus N dP dt, where N is the number of turns of the copper. Okay, that's N. So that's number of turns of copper. And then obviously phi dphi dt is the flux rate of change. With respect to time. This negative right here, why is this negative? The way, probably the easiest way to understand without getting too much into it is, if you're pushing a current through a conductor and you're establishing a field, there's an opposition to that change. There's an opposition to that change, and that opposition to the change in the equation is shown as a negative number right here, okay? So you can think of it, I have a current, and this current is creating a voltage or pressure that is pushing it back, hence in the equation this shows as a negative number. You'll see on some books, as a matter of fact, at the beginning of the chapters, they don't use this negative, but it is there, and that's basically what it's telling you. All right, so,
Professor?
yes,
This relates to Maxwell's equation, right?
correct.
Yeah.
remember the Maxwell equations?
Del cross, it's del cross E.
That's right, that's right. But the only, by the way, so the equations that we use are the watered down version of the Maxwell equations, okay? Yeah, you can use the Maxwell equations for that, right? The only difference is that some of the equations that we use are based on empirical. So we don't put all of the equation, all of the physics into it. It's just a watered down version of the Maxwell equations.
It's like simplified model.
Exactly. It's a simplified model, but it is true.
Because here you're taking a derivative versus a partial before.
That is correct. So it's a gradient, remember?
Yeah.
When you show on the Maxwell equation, because by the way, even the direction, right? Remember when you do the vector calculus, vector analysis? It's a dot product, by the way, right?
Cross.
It's a cross product. And that's right, because you're getting another vector, right?
Yeah.
Otherwise, you're getting a constant but yes, that's true. And the flux is not precise, right? I mean, you don't have all the arrows precisely in the same direction. So that's where the Maxwell equations, that kind of level of details comes into the Maxwell equation, whereas here, we're making some assumptions, right? So that's what I said is the watered down version of it. Okay, so with that, we can say the following. The derivative of the flux with respect to time, remember the flux is a sinusoid, meaning it changes because here it's being established by a current and a voltage that are sinusoidal in nature. So, two, we can say that assuming a sinusoidal flux, we can say that phi of t is equal to phi max sine omega t, right? The description or the shape of the waveform is basically the same shape as voltage and current with respect to time, right? And the other, I want to remind you of this. I see this in just about every book. They write the equation this way, and people get confused. They often think, is this a constant? I don't see the time. I don't see it as a function of time. I don't know why the book, the way the equation should be written is phi of t, right? Because it's a function of time. So if I take the derivative, once again, of that with respect to time, t p of t is equal to phi max, right? Omega cosine omega t, right? As a derivative. Let me ask this question. So this is a sinusoid, right? You all agree with me? If it's a sine, the derivative of sine is a cosine, right? What if it's a constant? Zero.
That's why when you say no, it's not moving. It's not doing
Exactly. So basically what is going on is this, right? If you can think of this flux, and the flux follows this, right? So it starts at zero, nothing, peaks, reverses, peaks, reverses. So flux is going this way, zero, the opposite. And it's doing this, right, with respect to time at 377 radians per second, right? Following the frequency of the system. If it was a year, it would be 50 hertz, right? But here 60 hertz. So basically, the way you can think of it is you have a magnet that is going like this, positive and north south, north south, north south. You can think that way, north south, north south. If I do this and I put a wire, this is a nail, and I have a voltage source. Remember I was talking about this the other day, and I said if I have a piece of metal right here, right, and I close this, I make this north and this south, right? So I have opposite poles and I'm doing this, right? It's only in one direction. The flux is unidirectional. That is the reason, because of this derivative. If you take the derivative of constant, you get zero. That's the reason why you cannot use DC. Because DC doesn't change, right? So the flux, the field, the voltage and the current are constant with respect to time. Hence, the derivative of constant is zero. So that's, from the mathematical standpoint, physical standpoint, that's the reason why you cannot use. If I take a transformer right here, I have a DC source. Because of this, I'm establishing a flux only in one direction. I'm not inducing anything here because I need to have something that changes with respect to time. Otherwise, I cannot achieve that induction. That was the whole thing between Nikola Tesla and Edison, right? That's like this little simple equation. Pretty much tells you that if you put a DC source on a transformer and you expect something on the secondary, you're gonna get zero, you get nothing.
No, you get something in first and then stop. There's no more flux. You charge up the inductor.
Yes. As a matter of fact, I will talk about this too. We're towards the end. I talk about how do you determine this. How do you estimate the parameters for a transformer? And there's two tests that we conduct. There's the short and open circuit test. And basically, that's kind of what we're doing. We're leaving one winding open right here. So we're just trying to push the flux here without having anything on that other side. But we'll get there. We'll get there. We're not there yet. All right. So I can then rewrite that equation, the EMF equation as follows. E is equal to N being the number of turns times this right here, which is P max omega cosine omega t. And I can then, then I can, with that, I can also write the flux density. Remember, this is, let me see if I'm not very good at drawing, but this is representing as following. If I take this and I take a cross-sectional area of that and I make it a square, this is cross-sectional area of the core. Right, basically with the flux lines, you can think of this. This arrow is going here, coming in here, coming in here. I'm sorry. I'm telling you, I'm not really good at this. I'm going to do it this way instead. Coming here, coming here, coming here. Remember we talked about this? And I said the area be perpendicular. How can I change the flux density? If I change the angle, right, of the surface area, that's one. If I push more current, right? Remember I said that? And if I have more turns, remember I talked about that? So that's the flux. That equation is talking about this little arrows. Obviously, we combine them into one. But there's another term that we talked about, which was the flux density. You remember that? B max. And B max is equal to the flux, maximum flux, divided by the cross-sectional area. So the more area you have, the more arrows you have within that area, the higher the density, right? Do that make sense, everybody?
Yes.
Right? And remember, we talk about also we talk about the relationship between H, also the field and the flux density when we're talking about the hysteresis. Remember that? Okay. So, but for now, we're gonna use this equation. So we say that why is this important? And the reason why is because this is mostly, by the way, what I'm going to do here is mostly what transformer designers use. It's a little bit watered down, but just to give us an idea. So we say that if Bmax becomes too high, the core, what happens to the core, everybody?
It's up.
I'm sorry?
It's up.
No, there's one more. Remember when I was saying,
Does it check?
you remember when I said, remember I said lines, if I increase the number of lines, I'm increasing the flux density.
It will escape, no?
No, what
Oh,
happens, you get saturated.
Oh,
Remember that? Remember we were talking about this curve? And I said, oh yeah, H and B.
Oh, the material cannot.
Exactly, the material cannot handle more. It is saturated. So if Bmax becomes too high, the core may saturate.
So you have effectively,
Lower efficiency.
yeah,
Say that again?
like you reach a threshold where you can't conduct.
Thank you. You want to make sure that the transformer is operating in the linear region of the hysteresis, right? That's really what it's boiling down to. If the flux density is too high, you saturate. No matter how much current you're putting, you're not developing voltage out of that transformer.
So you're losing.
Right. So, what will that result in? Well, number one, excessive magnetic currents, and we'll talk about this when we talk about the transformer models. Overheating, of course, overheating of the transformer core, distortion, and then last but not least, transformer can damage. Damage. So you have a limit of the flux density of the core, and you gotta keep it in check. So it's part of the design of the transformer. Now, so I said excessive, and we're gonna quantify this with the model. Overheating, we're gonna quantify this with the model. And then distortion is once again, right? I think I mentioned this, right? And I said this. If we drew this thing, right, hysteresis, and I said, well, we try to operate the transformer in this linear region, right? And I even mentioned that if you model this with that saturating basin, what you get, you don't see the hysteresis that you see on the old one, right? So this is respect to time. What happened is, and this is H again, this is the magnetic field, and this is B, the flux density. You can replace this with I, and then you can replace this with V, which is voltage. What I'm saying is, if you have a transformer, you push current right here, right? And if you start getting into this nonlinear region, you can continue to push the current, but the voltage will not increase. I can push and push and push more current, but the voltage will not change anymore. So that is what we talk about distortion, right? Basically if you look at the waveform on the secondary side of the transformer, if your core is saturated, the waveform might look like this, chop at the top.
It's eclipse.
Eclipse. You get to a point, you clip it, right? What happens when you have, you remember this waveform? This waveform.
You have
You lose harmonic.
DC source for momentary.
No, what I'm saying is, if this signal right here, assuming that I did a really good job and I made a precise sinusoid that is like this, V of t is equal to V max cosine omega t, right? Omega t. This frequency is 60 hertz. It's a perfect sinusoidal wave.
Create different harmonic.
That's right.
Yeah.
If you make a square, it's basically the result of a fundamental plus a bunch of harmonics. So when you're doing this, Even if you just cut just the very top of the waveform, you're creating harmonics, and that's how it's resulting. That's why when the transformer is energized for the first time, sometimes you do go to the nonlinear part of the transformer and you see that distortion. I'll do it on the simulation, by the way. Yes.
Can you damage components on the receiving end if you start to set harmonics that are not
Yeah.
within the,
Yeah.
anything more than the fundamental?
Yeah, you could, for the most part, loads are very resilient. But if you have a very, how do I say it? If there's certain loads that are very susceptible to harmonics or to any power quality, whether it's harmonics or what do you call it, sags or spikes, high frequency, you could damage the load, right? Go ahead.
Because you had mentioned that like any AC system that's powering a building or something, it has to be accurate to incredibly, I forget what was.
Frequency.
Yeah, the frequency itself, but then the signal itself changes, even though the frequency is the same.
And who's responsible for it? It's not the utility, the load is the one. Because the load is the one that has the nonlinearity. Do I make sense? So the utility is gonna give you 60 hertz.
Because it's the one that's transforming.
Exactly. Is the load the one that, for instance, if you have, say for instance, I'm gonna give, here's the utility. You have a transformer. And here's the load. And this is a switch mode power supply. Switch mode power supplies have the tendency to create harmonics, right? They're non-linear devices. So they reflect harmonics. So the transformer is the one seeing the harmonics, right? And the problem with that is that, remember, the harmonics is this. I fundamental plus I 60 times 3. I'm going to use add harmonics, not even. I 60 times 5. I 60 times 7. I can continue on into this, right?
Yeah.
You have a 60 hertz. The load is asking for that, but it's also asking for all of these other harmonics. These are currents. Current is a current. It doesn't matter what frequency, it's still I squared R losses. Do I make sense, everybody? So, from the when does the transformer misbehave? It has nothing to do with the load. Forget about the load. When will the transformer will misbehave if you get to the point where you saturate the core, where the transformer, the Bmax will exceed what the core is being designed for. Now you're starting to work in this nonlinear region. Now you're starting to see distortion. And overheating, yeah, because remember I told you how about those harmonics? Current is current. It doesn't matter what frequency it is. It's still current. So that's why, once again, that's the key thing, especially for transformer designers, to when they're designing around a specific what do you call it, flux density. We'll talk about that. I have a very simple exercise, nothing overly complicated. All right, so let's see. Let's say that the design of Bmax is chosen below, I'm sorry, the saturation region. And when I say I'm talking about the hysteresis curve that we talked about. So the equation that we get is equal to where do I have example? I actually have an example. Example. If we have a transformer where I need a voltage to be 230 volts and frequency that is being designed for 60 hertz, and the Bmax that this core that I'm designing can handle is 1.2 Teslas and no more. And then the cross-sectional area of the core is equal to 0.01 meter squared. So these are my requirements. And the question is, how many turns of copper do I need to achieve this with those requirements? So N, which is the number of turns, the equation.
Sorry, what unit is that? You said A is
10.
0.01 M what?
Oh, meter squared.
Oh,
It's a cross-sectional area.
got it.
It's the core.
I thought it was current. I was like,
Oh, sorry. It's the core.
thank you.
If you slice it, right?
Right.
What's the cross-sectional area? And so the equation is equal to E. Hold on one second, everybody. So I have, that's it, E divided by 4.44. I'll tell you what that comes from, but this one times B max times A. So N, or the number of turns, is equal to the E, or the voltage that I'm designing for, divided by 4.44 times frequency times B max times the cross-sectional area. So N is equal to 230, which is the voltage, 4.44, which is a constant. I'll tell you where that comes from in a minute. 60 hertz times 1.2 Teslas times 0.01 meter squared. So N is equal to 71.9 turns. Okay. If you're a transformer designer, they're giving you this information. Somebody design a core for you, and they tell you this is the cross-sectional area of the core. They're limiting you to this Bmax, and these are your frequency and voltages. You come up with a number of turns of 71.9. Okay, well, because we want to be precise numbers, you can say that this is actually approximately 72, right? So 72 turns. Yes, sir.
So that Bmax would be, I guess, the upper limit of what, before the saturation point, right?
Exactly.
Would you usually use that like an RMS version of, so root 2, one over root 2 of that number?
Yes.
Okay. Because you don't want to hit the peak.
It's already there.
Oh, I see.
It's already there. I'll give you that equation. That's a very good. Where does this 4.44 come? That comes from there. What you just said. Yeah, good point. But for now, what I was trying to say is this is the number of turns that I will be, obviously given these parameters, right? These parameters that I've been given. So what he was asking me is this, and I don't know why I did this, but I did. So that equation, you write it here. Yeah, I flip them. So E max is equal to N omega P max. Remember this equation, right? This is the RMS value. So what I'm going to say is that E max is also equal to N times omega, which is 2 pi F, right? To the N 2 pi F times P max. All right, so we're going to convert the E max, to E RMS. Okay, so we know that E RMS is equal to E max divided by, let's remember, square root of 2, right? Okay, so I'm gonna substitute that, and I'm going to say that now I'm gonna write it here, raise it so I don't get this convoluted. I'm gonna say that E is equal to 2 pi F times N. Phi of flux maximum or peak divided by square root of 2, which is the RMS value. I want the RMS value of this. That gives me 2 pi over square root of 2. 2 pi over square root of 2 is approximately 4.44. That then becomes ERMS is equal to 4.44 if n feet.
Oh, I see, that's where it comes from.
P max. I'm sorry, I hesitated for a second. That's the equation. I derived it. I did this before deriving the equation, but do you see where it comes from now? All right. So this is the equation transformer designers will use. Let me see what I was going to say on this. So that's obviously, there's a lot that goes into it, right? I mean, not only the number of turns, but the biggest thing here, one of the critical things here, in addition to that, that's dictated by the material, by the way, right? Depending on the material that we're using. Remember we were talking about hysteresis, and I was saying depending on the kind of material, you can have the hysteresis to the shape to be either very thin. Remember we were talking about that last time? So that, and that's what I said, right? That depends on the material. So if the material, something that is dictated by that. This right here is the geometry of it, right? So how much core material do I need? And obviously, there are softwares that are used. Oh man, I forget the name of it. There's a software that a lot of schools used to have it. I don't know if they still have it, but to design transformer, they use methodological. What's the name of it? Oh God, they use the same mathematical model in fluids. Oh geez, it will come back.
Like, is it for CFD, like computational fluid dynamics?
Yeah, you know, there's a mathematical model, and there's softwares that use, like in fluid dynamics, they use that a lot, where you break something into very small, into small pieces.
Is it maybe a Stokes equation?
Oh God, the word came out.
You can do it.
It'll come back. The softwares that they use, they're based on that equation, by the way, but the softwares that they use are different from what we use for electrical analysis, right? This is more for magnetic analysis. That a lot of the people who do the design will use, but there, once again, point I'm trying to make is based on this equation, all right? And the geometry, you can change the geometry and you can see the magnetic field, you can see the flux and how it will behave, and then you can change the type of materials as well when you're doing the design. So a lot of the design uses that. I'll remember. Okay, so we got that equation. I have another example. All right, yeah, another example. So if, oh, by the way, I tell you where else you're gonna find this. This is for power transformer, for instrumentation transformers. You use the same equation, and where they use this, when you talk about instrumentation transformers, is when the engineers are trying to find out whether a CT or current transformer will saturate or not. How do they determine whether they're going to have a saturation? So they often know the cross-sectional area, the voltage, and the frequency, and then they're trying to see how far in the current, or how much current can I push through the current transformer before it gets saturated. So they call it the formula method. All right, so another example. If a transformer is designed on the following, based on the following specifications or specs. V primary, 230 volts. V secondary, 120 volts. Frequency, 60 hertz. The rating or the VA rating, volt amperes or S, right, is equal to magnitude, by the way, is 120 volt amperes or VA, and the V max will be 1.2 Teslas. That's the requirement. And the cross-sectional area that we have is about 0.0025 meter squared. So those are the parameters that are given to us. And the question is, well, there's a couple of questions. So for this transformer, can you at least give me some idea of following? Find primary number of turns required, number of turns, secondary number of turns. What is the primary current? Primary current. What is the secondary current for this transformer? Current. I'm just going to leave it there. So these are the questions. So here's the parameters that I have. Can you tell me for this transformer with this given parameters, how many turns of copper do I need in the primary and the secondary of that transformer? That's really the question. Using that equation that we're giving now, what I was going to say is that this is just an approximation. By the way, as I told you, if you're actually designing a transformer based on that equation, this just gives you an estimation, right? Obviously, you got to run this whole design through a much rigorous process. It's not just that simple, but it can give you an idea. Okay, so E again equal to 4.44 F N V max A. By the way, I feel like I forgot on that formula an A. I feel like I forgot. Did I give you a formula?
No.
No, okay. I look at this one, because I corrected this one, I thought maybe this is the old one. Okay, so we're gonna solve for this, right? In primary, which is equal to V primary, which is E, right? I'm gonna put this here so that you don't be confused. VP and EP are the same. Divided by 4.44 V max A cross-sectional area times the frequency. So the number of terms is equal to 230. I don't have to put volts, times 4.44. What was the Teslas? 1.2 Teslas, 60 hertz, that doesn't change. And the cross-sectional area is 0.0025 meters squares. So I get N is equal to 287.8 turns, so I can round that up to a whole number. And I can say that in primary, I need 288 turns of copper on the primary. Now, that doesn't mean, that's just a turns ratio, by the way. That doesn't mean that you are gonna have, that doesn't mean that you're gonna have 288. You can double it, you can triple it. But if you double it, you gotta double the number of turns on the secondary. Do I make sense?
Yes.
It's just a ratio.
That's a ratio.
If the ratio is not maintained, then you'll pass the max.
That's right. If the ratio is not maintained, well, you can think of it as this. Let me make it a very, very simplistic example here. Say I have a transformer here, and they give me those requirements, and here it is, and I say, okay, well, they're telling me that I have a transformer that requires 100 turns on the primary ratio. Turns, let's start with turns. I have 100 turns right here, which is the next step we're gonna do here. And they're asking me, what about the secondary? Well, the secondary, for that design, I need 10 turns on the secondary.
So then,
I can have 220. Do I make sense?
but to say
Physically.
you should do 10 and 1, right?
Well, yeah, there's multiple ways to slice this one. What I'm saying is, if I have 100 turns of copper on this side, and I have precisely 10 turns on this side, now I come here and I apply 100 volts. Here, how many volts do I get here?
10.
10 volts. Do I make sense?
Yeah. Sorry, go ahead.
Go ahead.
I was just gonna ask, like, if you were to do 1,000 and 100 or 10,000 and 1,000, like, would there be a benefit in having the same ratio but just at a higher scale?
Yes, because you have more copper,
So more carrying capacity.
more, exactly. That is just telling me what is the number of turns.
Okay,
I-
that just determine the voltage, but if you have higher current, you need more turn to carry that current. Is that right? Is that what you're saying?
No, we're looking at from the energy dissipation point of view, right? You put more wire, you have more, I'm gonna say more cross-sectional area, I'm gonna put it that way, right? So I have more, I can transfer more energy, that's what I'm trying to say. But to maintain the voltage, I gotta maintain the number of turns. For instance, let me say it again. So if I have 200 right here, turns, and 20 turns right here, and I apply 100 volts right here,
Then you will
10
still get
volts.
10 volts.
10 volts.
right? I get 10 volts. You follow what I'm saying?
Yes.
Okay, but this circuit, you can carry more power.
Exactly what I'm trying to say is that now, because I'm increasing the amount of copper, I can deal with more power, right? Now, the designers, I'm pretty sure they don't do precisely 100. We're gonna talk about voltage losses on it, right? They might wanna extend it a little bit to account for some of the voltage losses on the copper. So, but what I'm trying to tell is with this equation, this is usually what a transformer designer, when you go to them for the first time, I used to work for Schneider, we have our own transformer design, this guy was amazing. I used to go to him and say, hey, forgot his name, it's been so long. This company, they want us to design a transformer, and I will give him all the specifications, blah, blah, blah. And the question that I often have for him is, can it fit in the cabinet, right? Because we had cabinets, and it was UPSs, right? And basically that's how he will do it. He'll take that equation, and he said, all right, let me check it out. Boom, 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 boom. Yeah, I think it will fit. I think you'll be fine. I think we can design it. That is what I call, once again, it's kind of like on a napkin, right? But when you go the actual design, You're gonna use those parameters, but you need a software because there's a lot more that goes into it, right? As you're designing the core, the geometry of the core and all that. So anyway, but do I make sense, everybody? So this is just giving you, once again, the people that I use this equation, really, I see them as protection engineers when they're looking at the saturation of current transformers. They use the formula method sometimes to determine whether, because they have all that information. They just want to know, am I going to saturate this CT or not? And for them, it's really important because if you saturate, the relay doesn't see the current that is supposed to be seen, right? Let's see. All right, so what do we do? So we got this. We got the number of turns. What about the secondary? I'm going to jump ahead because I'm going to come back to these equations, but I'll give you a preview. V primary divided by V secondary is equal to number of turns on the secondary divided, number of turns on the second, the other way around, see, it's the same thing, primary. V secondary divided by V primary is equal to N secondary, or turns on the secondary, divided by the number of turns on the primary.
It reminds me of the torque and gear ratio equation.
Say that
It's the
again?
same thing.
The torque and the gear
Yeah,
ratio equation.
exactly, but he said the same thing, it's a ratio, right?
You said in control.
Yeah, yeah. It is the same, well, not the same thing, what I'm saying is the same
Concept.
Well, they
concept,
transfer energy in the same way.
right? From gears, right?
Yeah.
So the larger the gears,
I think in our controls class, we transferred electric circuits to gears and then solved it in the S domain. The same kind of.
there is a software, and I'm glad you guys said that, because there is a software called EMTP to do electromagnetic transient analysis. And we didn't have machines. And instead of using a rotating mass sometimes just to do the analysis, we'll use
Electric.
mechanical, like storage, you use like a pump. You follow what I'm saying?
Like a spring or a.
Spring,
Yeah.
exactly. So it's it's analogous, I'm gonna say. All right, so we know, so now I'm doing the primary, right? I know this, right? They give it to me. Both the secondary. I now have the primary number of turns. I know this voltage I can solve for this. Do you agree with me?
Yes.
So I can say that number of turns of the secondary for this transformer design, I remember finite elements. You guys remember that? Finite elements, that's when you take something and you break it into small little pieces. It's a mathematical tool, a mathematical analysis. That's what they use to do this. They use finite element softwares. And I said schools used to have it, right?
Oh, that's what the name's called?
Finite elements is the mathematical method. You guys remember that?
No.
You guys do thermodynamics?
I know FE.
No,
like
we don't do
finite
thermodynamics.
You
element
guys don't take it anymore, right?
No.
Yeah, I remember vaguely, but I do remember that.
We're too lazy to learn those things.
The primary. So this is equal to 200, what do we count, 288, more or less, round it up. And then the voltage on the secondary, 112 volts. And the voltage on the primary is 230, that doesn't change. So the number of turns on the secondary comes up to be
12 volts or
about
120?
15 turns.
120 question mark?
I'm sorry?
120 question mark?
One,
Yes, is 120 question mark?
288, 12 divided by 230.
120?
Oh, yeah,
question mark?
120. VS is 120.
120?
Oh,
What?
You were.
hold on.
Wait.
Yeah,
Just add a 0.
did I, why did I put 12?
You're solving for the secondary.
That's correct. I solved from the secondary. Okay, so I get 15. Is that what you guys did? Can somebody do this? Maybe I created this problem and I messed it up probably. Let me see.
Oh, 150.
Huh?
It's 150.
It's 150, right?
I got the same thing.
So 288 then, 150?
That's probably that 0 you were missing.
Ah, okay. 150. All right. So this is basically, once again, I'm gonna go here. If you think about it, once again, I can do 150 turns of copper. I'm sorry, 288 and 150. But can I double this? Can I triple this? Yeah, but if I double this and I triple this, I have to double this and I triple this. Do I make sense, everybody? That's just what we call the turns ratio.
And the doubling and tripling depends on how much power you need.
Right, I mean, and that's part of, like I told you, the full design of the transformer, right? The engineer designed the transformer. By the way, transformers to do electromagnetics, yeah, they're electrical engineers, just like us, but they're trained in a little bit differently than we are. Because that's what they do, they have to deal with the geometry of it, they have to deal with
So
the electromagnetic
So they're physicists.
equation. I'm sorry?
So they're physicists, right?
In a way, I mean, yeah. Let's see. What was the other question? Oh, the primary and the secondary currents. All right, so now that we have that, and I'll come back to these equations again because we're gonna use them for a different type of exercises. But for now, what they're saying is equal to 120 volt amperes, right? So if I go and I said I primary is equal to volt amperes divided by volts on the primary, and I said that it was 120 volt amperes divided by 230 volts, so I get, can you guys check this number on me? Like I said, I made up this example and I didn't, now I'm doubting
Did
myself.
you make the example
Yeah,
before
I think it is.
accident or
I think
after
it
the
is.
accident?
I think it is.
Okay, just like-
0.552. Okay, now, let me ask this question. So this is the 230 volt side. What about the secondary? So I have, the VA is the same, right? Remember, I'm transferring volt amperes from one side to the other. Do I make sense, everybody? And I'm saying this transformer is a perfect transformer that doesn't have any losses. So whatever I put in, I get out. All right, so in this case, I said it's 120 volt amperes divided by 120 volts is equal to how many amps? 1, right? Now, let me ask this question, everybody. Which one needs a thicker wire and which one needs a thinner wire?
And secondary?
The secondary needs a thicker wire. Remember we were talking about that? And I said, when I was looking at, I'll show you the transformer, the insulators, and I said, well, the separation between them, because you want to maintain a distance between the two potentials, right? The larger the voltage, the more distance you need, right? If you start bringing them close, now you're going to have a breakdown of the insulation. What's the insulation between the two insulators? Air. There's no plastic, there is nothing, air. So you can have a breakdown, right? So you need a lot of spacing. But when it comes to current, you transfer the same amount of energy from one side to the other. Say you're getting 99.9% on the other side. As you lower the voltage, you increase the current, so you need a thicker wire.
Proportion,
Huh?
it's proportion.
Yes.
Because the power is fixed.
I'll come back to this. By the way, as I said, this is just to give you an idea. So obviously somebody needs to design the core. I gotta tell you what the core is. And remember we talked about the BMAX. That, it depends. I mean, how much money do you have? How much money you wanna spend? What is the quality of the core material, right? So that depends on all that. Oh, sometimes it's even what application is this device? For instance, if it's a power transformer, different from an instrumentation transformer, if an instrumentation transformer is going to experience very high currents, and that's why you want it to work. Do I make sense? So the Bmax, or the saturation curve for that, say for instance, if you have I'm gonna use the line like this. I'm gonna say this is 10, this is 20. This is what I was trying to say. So if you have a power transformer, right, you're gonna run it in this region, right, constantly, right? Your transformer can only go by a few amps above its rating, right? You say the transformer is rated for 100 amps.
What are the units on the axes for that?
100 amps.
No, the X and Y, what are they?
This is current,
High voltage?
and this is gonna be voltage, right? I'm gonna say it's current and voltage. So a power transformer is always, most of its life is gonna be in this region, right? So transformer is rated for 1 amp, 120 VA is 1 amp of the secondary. What it's rated for? Can you increase the current on the secondary of the transformer to 1.5 amps? Yeah, probably, yeah, right? Can you do it forever? Maybe not, right? You have margins that you can play with depending on the design. When you buy a transformer, you say, I want a transformer that's rated for 1 amp plus minus 5%. And oftentimes, even transformers, they say, oh, I want to run the transformer at 130% of its rated value for 1 hour. And the transformation, okay, run it for 130 amps for 1 hour, but then you got to bring it down, otherwise you're going to start damaging it, right? But the transformer throughout its life is just very steady as far as the currents that it's going to see, right? So you want it to perform in that linear region and doesn't deviate too far. If you're using this transformer and the primary of the transformer is a wire and the secondary of the transformer is a current transformer that is going to be connected to a protection device, the current under normal operating conditions, all day, all night is going here. But when the fault comes, when you have a fault on the system, the current is going to go. So that transformer better be able to have a very wide linear region, because that is going to result into very high currents that you want to be able to get a voltage out of this that is not distorted, because the relay wants to see it. Do I make sense, everybody? I'll give you another one. Instrumentation transformer, there's also revenue transformers. That's what you have at your house. You have a revenue transformer. That's where the utility is charging you, right? So that transformer, who cares? I don't care whether it saturates when there's a fault, because it's going to be clear. I want the transformer not only to be as precise in this linear steady-state region as a power transformer, but the precision of it needs to be, because too much deviation from the actual current results into the money that you have to pay. Do I make sense, everybody? So you can think of, when you're operating a transformer, you are designing the transformer you can be designed for different applications. As a power transformer, as an instrumentation transformer, where it's going to experience very high currents, even if it doesn't perform as good on a steady state. I want it to do it at its best when the current increases and it goes very high. And then the last one, which is a revenue transformer. If you're designing that transformer, you want that transformer to be as precise as possible when it comes to current and voltage that is measurement, because that's going to result in the power that it measures, which is the money that you're going to be paying the utility. So it depends on the application, and that's the equation basically that they probably that's the equation that they start with when they're designing a transformer. How much time do I have, everybody?
10 minutes.
10 minutes. Oh, let me see. 10 minutes, 10 minutes. Okay, let me say this, because there's so much material that I will not test you on this. I just kind of want to give you an idea. Just an idea. If everybody ever asks you, like, hey, here's an example. How do I design this? You at least have an understanding, but it doesn't come across a lot. if you will work for one of these companies that I told you, at the design transformer, there's gonna come up, they'll train you on that. And they use, like I said, really,
But this is on the exam.
this is not gonna be an exam, I'm not gonna test you.
Even the equation that you just showed us.
No, I'm not gonna test you. I'm gonna test you because it's a lot more other stuff that I need to test you for what I want you to be, up to speed on when you leave from here. All right. Any questions, anybody? I will work on your test this weekend and I will have it ready for you next week. I might have it ready before, because what I do is I grade it. Oh, I'm gonna do this because it's a lot easier. I grade the exam